In this problem, we're told about two electrically charged particles, A and B. We are given the magnitude of the force between the two particles due to their electrostatic charge at one distance apart, 13.7 millimeters, and then we're told that a different force is exerted when the distance between the two particles becomes 17.7 millimeters. We have been asked to find the magnitude of the new electrostatic force at that new distance, at that distance of 17.7 millimeters. Now, normally, when we're trying to analyze the electrostatic force between two charged particles, we can use Coulomb's law, which states that the electrostatic force is equal to the Coulomb constant, K, multiplied by the product of the two charges, we'd call them Q sub 1 and Q sub 2, divided by the square of the distance between them. In the case of this problem, however, we cannot use this formula directly because we haven't been given the magnitude of the charge on either of the two relevant particles. We've only been told the force for one distance, and then we were told that the distance has changed. We can still use Coulomb's law to solve this problem, but we'll have to do it indirectly using a ratio. Let's say that the initial force between the two particles when the distance is 13.7 millimeters is F sub I, or F initial, and we'll say that the second force for when the distance between them is 17.7 millimeters is F sub F, the force final. The ratio of the final force to the initial force is F sub small f divided by F sub I, the final force divided by the initial force. So to find this ratio, or to expand on this ratio, we're going to plug in a different version of Coulomb's law for the numerator and the denominator of this ratio. So for the final force, we've got the Coulomb constant multiplied by the product of the squares, Q1 times Q2, divided by the final distance between the two particles, or R sub F, squared. And this is divided by the same Coulomb equation, but now for the initial case, where the distance is R sub I, the initial distance. So again, that's the Coulomb constant K, multiplied by the product of the same two charges, because the magnitude of the charges have not changed, we're still dealing with the same two particles, divided by R sub I squared, the square of the initial distance between them. Now right off the bat, we can see that several of these variables will cancel out because they're the same. The k's will cancel out, the q's will cancel out, and all we're left with is 1 over r sub f squared divided by 1 over r sub I squared. So the r sub f goes into the denominator because we have a 1 over it even in the numerator. And in the denominator, we have, again, a reciprocal r sub I squared. So that becomes relocated to the numerator. So we've got r sub I squared in the numerator, which I would argue can be more simply written as just r sub I over r sub f within parentheses with a square adjusting the entire term. And in order to solve for F sub small f, the final force, all we need to do is algebraically multiply both sides of the equation by F sub I. It's pretty simple algebra. In doing so, we find that F sub f is equal to F sub I multiplied by the square of R sub I divided by R sub f. All that's left for us now is to plug our values that were given by the problem into the calculator. So F sub I is given in the problem as 2.62 newtons. Then we're multiplying by the square of R sub I over R sub f. So the initial distance is 13.7 millimeters divided by 17.7 millimeters. And note that there's no reason to do any unit conversion on the distance in this case because we've got millimeters over millimeters. So those units completely cancel out. Even if we were to convert those distances into meters, it wouldn't matter anyway because that ratio isn't going to change. But if we put this into a calculator, we find a magnitude of the final force of 1.57 newtons. Note, however, that we still have not yet fully answered the question. We found the magnitude of the new force between the particles, but the problem is also asking for the vector force, meaning we can't only specify magnitude, we also have to specify the direction of the force. Meaning we need to tell the problem which direction the final vector force is that B exerts on A. Now note from the background information given in the problem that the charged particle A exerts a force to the right on the charged particle B, which causes the particles to move farther apart. This means that we have a repulsive force. There is an electrically repulsive force between the two charged particles. So particle A is going to exert a force on particle B that will push particle B to the right, away from particle A. And as per Newton's third law, particle B must be exerting a force on particle A that has equal magnitude but in the opposite direction. So if particle A is pushing particle B to the right, then particle B must be pushing particle A to the left. So the final answer to our problem about the vector force of particle B on particle A is that it has a magnitude of 1.57 newtons that is directed to the left. And that is our answer to this problem. And that is it for this video. I hope this video helped you out, and if it did, please consider subscribing, as that'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below, and I'll do my best to help you out as best as I can. That's all for now, and I hope you all have a lovely day. Bye-bye.